Hello class, this is CSE-5250. Is this thing recording? I think it broke. Okay, I think it's recording now. Hello class, this is CSE-5250, Section 1 and 60, Week 10, Fall 2023. So this week's video may be a little bit shorter, and that was because I had to be out of town for part of the week. So for this week, I'm giving you a few lighter assignments for you to work on. The first one is a short answer question. The second one is related to p-threads, where I showed you in a past video how bad it is to use busy waiting in a p-threads program, and why, generally speaking, we never want to use that in an actual program. But before we get to that, I would like to go through the next set of slides regarding MPI. Because eventually we need to, for our final project, your midterm project is to write the sieve of Eratosthenes using OpenMP and seeing whether we can reduce our execution time. Your final project is doing the same thing, but instead we are using MPI for that. So, let's look into the next set of slides for MPI and see if we can understand how we can, for example, get user input into an MPI program. Right. I will say right now it's basically the trapezoid rule from chapter 5. But before we get into that, here's a short answer question that I want you to answer. So this is the Hello World program from when we started looking at MPI. And this question is pulled from the textbook. It's on page 148. What would happen if, on line 19, the second argument is stir-len greeting plus 1, and that is the size of the message in bytes? What if instead we took out that plus 1? What would happen if we sent a message without that plus 1? And then what would happen if we sent in the message using max string, which is defined on line 5? What if we used max string instead as the second argument of the MPI send function here? So, play around with this program, take out the plus 1, see what happens, and then replace the whole thing with max string instead, see what happens. Can you also explain what's going on? This short answer question is structured a little bit differently. So instead of it being divided into two parts where you would make a prediction and then follow it up as part of a homework assignment, I'm just condensing the whole thing down into one single question. So the answer for this question, you are to, well, provide a screenshot of what's going on, and then write an explanation of what's happening. You'll actually need two screenshots because I'm asking you to replace that second argument with two different things. So that is your short answer question. It's basically play around with this program and see what happens if you replace that second argument with stir-len greeting without the plus 1 and try it again with max string instead of stir-len greeting plus 1. So that's your short answer question. We're coming back to the trapezoidal rule, which we first looked at when we were looking at OpenMP. The trapezoidal rule, if you recall, is a means of estimating the area under a curve. And in the context of, say, a calculus class, we would do this process of dividing the area under a curve into finitely many trapezoids. And then we would repeatedly do this process with more and more and more trapezoids until we are adding infinitely many trapezoids. And then through the power of integral calculus, we would say that that infinite sum equals an integral, and then we would use the rules of integration instead to find the area under a curve. We're not really doing calculus here, so instead we are simply estimating the area under a curve using a finite number of trapezoids. Once again, here's the area of one single trapezoid, but we are adding the area of multiple consecutive trapezoids, one after the other. We looked at this back in chapter 5, but I'm just going to say right now, the 4-step process here, described here, it applies no matter what kind of library we are using. So it doesn't matter if it's MPI or OpenMP. We are to partition the problem solution into tasks, identify communication channels between tasks, aggregate the tasks into composite tasks, and map composite tasks onto cores. So partition the problem solution into tasks. Say we are adding 1024 trapezoids, but we have, say, 4 processes. So we would assign 256 consecutive trapezoids to one of the 4 processes. Each one would aggregate. I actually missed a step. There is no communication yet, but the idea is each process would then add up its share of 256 trapezoids together, and then it would somehow need to communicate that to another process so that that process can add up each process's individual areas together. If I can show you what that looks like, in fact, I'll show it to you right now, graphically. Okay, so we have an area under a curve that is divided into some number of trapezoids. Say it's this interval here. Pretend each of these sections is divided into smaller trapezoids, and we are assigning each section to an individual process. P0, P1, P2, P3. Each process is going to add up its share of trapezoids into an area. So let's call it area 0, area 1, area 2, area 3. Okay, but now we have all the individual areas, but they're not added together. So we need a means of communicating all of these individual areas to one process. We're going to do that by sending all these areas to process 0. So that process 0 is going to add area 0 with area 1, area 2, and area 3, so we get the total area. So this is basically what we're doing. We are dividing the area under a curve into a series of trapezoids. We're giving out sections of those trapezoids to individual processes. Each individual process will find its own area, but they need to send all of those areas back to one process, so that process can then add all the areas together, and then we can get our total area. So that's what we're doing. We're partitioning the problem. We are identifying communication channels between tasks. We're aggregating tasks into composite tasks, and then we're mapping those onto cores. So that's the general process of how we can create a parallel program. So here, in fact, the first slide here has the first 10 lines of code for our trapezoid program. Our next slide contains the next 20 or so lines of code after that. We are going to estimate the area under a curve using 1024 trapezoids. This is hard-coded for now. We will get back into having the user specify any number of trapezoids later on. We are also hard-coding the interval to be between 0 and 3. Again, we'll get back to that later on. There are some special considerations when it comes to having user input be entered using an MPI-based program. But for now, we are going to define a handful of variables: my rank, com size, n, that's the number of trapezoids. We're hard-coding that to 1024. We also have a local n. We are also defining the bounds of our interval to be from A to B, and we are hard-coding those variables as well for now. We also have h. We'll get back to that later on. We also have a local A and a local B. We are also defining a local int. Local int and total int are the areas of our trapezoids, but the local int represents one of the individual areas here. So local int is going to be, say, one of these individual areas. Total int is going to be the sum of all of those individual areas. And we also have something called source. We'll get into that a little bit later. Before we do anything related with MPI, of course we have to call MPI init. And then we can assign values to our variables com size and my rank. Remember that the com size is how many processes are in a communicator. And a communicator is a set of processes that can all talk to one another via messages. My rank is you can think of it as a process ID for a process, but it's within a communicator. We're only dealing with one communicator, so you can think of it as a process ID for now. So now we got our com size and rank. We can begin with the area calculation. So we need to first calculate h, and then we can calculate local n and local a and local b, and then using local a, local b, local n, and h, we can then calculate our local int. That's the area of a portion of the trapezoids that one process is calculating. That's calculated using a function called a trap. And we defined that last slide. Or rather, we've defined a function prototype for that. So it has 4 arguments: left endpoint, right endpoint, trapezoid count, and base length. It's going to use a function that we define on line 9. That function is going to be f of x equals x squared. We could use any function that's well defined, but let's just stick with f of x equals x squared because it's a simple function that we can understand. So as you can tell, we have a few variables that we can consider to be local variables, as well as others that we can think of as being global variables. Some of them are pretty obvious because they have local in the name, but others not so much because h is a value that would be the same between all processes. But local A and local B, each process is going to have a different value for those. So let's proceed with the code. So here's the next section of code. So let's look here. This is the part of the program where we are calculating the areas of our consecutive trapezoids. But the next step is to communicate that information to one of the processes so that process can add up all of the individual local areas into one total area. So here's the next set of code. We are delegating the task of adding all the individual areas to process 0. All other processes will need to send that local area, its local int, over to, it'll have to send that information to process 0, and then process 0 must add up all of those areas into one total area. So it means that for nearly all the processes, it is not going to touch total int at all. Only process 0 is going to touch its total int. And by touch, I mean it's going to assign a value to it, where it starts with, process 0 starts with assigning total int the value of its local int. And then, as it receives messages from all other processes, it's going to increment its total int with that process's local int. So we're overwriting process 0's local int with whatever another process had calculated for its local int. And then we're incrementing total int with that value. But at the end, we can print out our area, and then to be absolutely sure, we can run this through an integration calculator to make sure we had the right answer. And then once we're done, we can call MPI finalize, and we're done with the program. But that's not the end of the code, because we also have 2 more functions that we have to define. We had the function prototypes, we had to define the functions after that. So here are the function definitions. Trap, as I mentioned, is a function where given a left endpoint, right endpoint, trapezoid count, and base length, it's going to calculate the area of consecutive trapezoids. And the lengths and the area of that trapezoid is dependent on whatever f of x evaluates to. So f of x, we are just using a simple quadratic of x times itself, or x squared. There are some simplifications here for the sake of making the calculation easier to do for the computer, but the point is we are adding trapezoid after trapezoid, and then returning that total area as an estimate. Those estimates return those estimates are calculated once per process, and then those processes send them to process 0 to be added together. Once we're done writing that program, we can compile it and run the program using the command mpi exec. The command to run these MPI programs is a little bit different. But here I have a slide showing what that command looks like. So it's mpi exec -n, the number of processes, and then the name of the executable. We are hard coding the interval and the number of trapezoids for now, but I'll show you what it looks like if we were to instead have user input, because there are a few considerations for that. And here are the considerations right now. We're dealing with I/O in our MPI programs. If we were dealing with one process, that is okay. But what if you have multiple processes? Who are you talking to, if that makes sense? Which process are you talking to when you are doing I/O? Of course, we'd like to have our program run with more than just hard-coded values. We would like to have the user specify their own values. In terms of output, all processes have access to standard out and standard error, which means that every process in MPI-COM world can print stuff to the console using printf. There is a demo program in the textbook where we have each process asking other processes, does anyone have a toothpick? Yeah, that's the example program. That's the example program that demonstrates how each process can print its own output to the console. Of course, the issue is there is no automatic scheduling, so each process will end up printing to the console something, but there is no order to it. Each process is basically competing for access to standard out, and the result is a random order every time you run the program, which is referred to the textbook as non-deterministic output. It's random. In fact, I'd like to demo that short program. I'll be back in a bit. Alright, so I have the program quickly written up here. The next thing I have to do is tell Visual Studio, hey, we have a few extra libraries you need to add. So additional include directories, edit, additional include directories, I need to add in the path that goes to program files x86, Microsoft SDKs, MPI, include. That whole folder. You don't have to pick x86 or x64, you just have to add the entire include folder. Select. Okay. And then linker, we need hold on. We need additional include directories. We also need additional library directories. Edit that. Additional library directories. Add in. Go back to the folder that has the Microsoft SDKs MPI lib. And then, depending on whether you have a 32-bit or 64-bit program, you either pick x86 for 32-bit or x64 for 64-bit. I'm selecting the x86 folder because that's what I have here. Select. Okay. And then input. Hold on. Additional dependencies. Edit. Type in msmpi.lib. Apply. Okay. Now if I built that program, build failed again. Uninitialized local variables, and that was because I forgot to call MPI com size and com rank. So let me just add that back in real quick. And by that I mean I'm just going to copy and paste it from another program. Build that. Build started. Build succeeded. For us to run this program, we need to right-click the solution itself, open folder in File Explorer, a window will open. I want to go to wherever the executable lives. So that would be not that one, or that one. Rather, we want just debug folder. And there it is. So I want to type in PowerShell into the address bar, and then type in the command to run this thing. I'm just gonna run this with, say, 20 processes. And now I can type in npi toothpick.exe. Does anyone have a toothpick? Says one process to another process. So this is the non-deterministic output I was talking about. There is no order to it. But every one of these is being printed by one of the processes that we have here. One of the 20 processes is saying, does anyone have a toothpick? So my point is, every process has the ability to print stuff to the console. So every process can do output to the console. But what about input? Let's go back to the slides. And okay, this is another way we can observe non-deterministic output, but I'd like to get to how does an MPI-based program handle user input? Well, in terms of input, most MPI implementations only allow process 0 to have access to standard in. If any other process needs that information being passed into process 0, process 0 must send that information via message passing. So here is some example code in which we have a get input function where if the function were to be called by process 0, it is going to use scanf to basically receive input from the user. Then it's going to send all that information to all other processes. And this is the code to be executed by rank 0. For any other process whose rank is not 0, it is instead going to receive whatever process 0 was given. So, this is the code we would use if we want user input, but the constraints are that only process 0 can do something like scanf. Any other processes must get that information via message passing. So this is our function that would handle all of that. So I am going to quickly modify the program. Actually, before I get to that, when we call this get input function, we need to, of course, call this after we have called, say, MPI init, but also after we've called MPI comRank and comSize, because we need those. So this would be no longer using hard-coded values for A, B, and N. Now we're using whatever values we want. So that's it on the slides, but I would like to show you what the MPI program would look like using the trapezoid rule. So I'm going to stop the recording for a bit and show you that. Alright, so here is our program that contains our trapezoid rule program. This is the trapezoid rule program. So I'm going to demo it right now by pressing Ctrl-Shift-B to build the program. Build succeeded. Perfect. Now I'm going to right-click here, open folder in File Explorer. My webcam may have obscured that a little bit, but let's find the debug folder, and there's our executable. I'm going to type in PowerShell, and now I have an instance of PowerShell where I can simply just type in npi exec. And one of the other caveats that wasn't mentioned in the program is when we divide our area into trapezoids, we must divide it into a quantity of trapezoids that is also divisible by the number of threads. So for example, if we want 1024 trapezoids, we need a quantity of threads that can perfectly divide 1024. So let's do 8 threads. Why not? 16 would also work. because 16 also perfectly divides 1024 without any remainders. So I'm gonna start with 8 threads for now and type in CSE-5250 MPI fall 2023.exe. I got an error. Won't be scheduled. Chunk size is not a valid positive integer. Debug session failed. Okay, let me debug that real quick. Okay, I found the issue. I was using the wrong code. So let's try that again. And since I have PowerShell opened up, let's type that in again. And now we have an area for the interval 0 to 3 and evaluated to 9 point something. But if we were to double check this with an online calculator, or if we know how to integrate f of x equals x squared, and then evaluate for the interval between 0 and 3, we would get exactly 9. So we can say that our program works. But the problem is, it is hard-coded, so we cannot do any sort of custom input. We can't input a custom interval, we cannot input a custom number of trapezoids. So we can fix that by following the steps shown in the PowerPoint slide, where we add in a get input function. So I'm going to show that by typing in void get input, and then the parameters are int my rank, int com size, double star a underscore p, where we're not dealing with a double, we're we're dealing with a pointer to a double. So that's what the underscore p means here. So double a underscore p, double star b underscore p, int star n underscore p. So function to receive input from the user, and then we need to define this function at the bottom. So to make sure the video doesn't feel too boring, I'm going to pause it and then just write out all the code. Alright, so here is the modified program. We have a function prototype for the get input function. We are calling it after we've called MPI init, MPI com size, and MPI com rank, and before we do all of the area calculations here. We are passing to the get input function the following variables: my rank, com size, and the address of A, the address of B, and the address of N. All the other calculations are otherwise the same. So the other change here is we need to define our get input function, where if you are rank 0, you are to receive input using scanf, technically scanfs, and then send that input to all other processes. If you are any other process but process 0, you're going to receive messages instead that contains those inputs. Oh, by the way, this dest variable here, it's used for the for loop. Typically, when we write for loops, we might want to write in for I equals 1, for int I equals 1. What we're doing here is defining the variable beforehand, and then using that as part of the for loop. So that is what also this source variable is here. It is part of it's supposed to be part of a for loop, but actually turns out I never used it. I instead had int I equals 1 when it could be source equals 1 instead. So that's what this dest here is. So I guess that's one weird error in the code that doesn't really affect the execution of the code. It is a habit of me to use for int I equals something as part of a for loop. So that's why we have source going unused. But it doesn't really affect the execution of the program. Really, we're more concerned with, does the program work now? I have PowerShell still open from when I was previously running the program. Let's run it again. Okay, there might be an issue where nothing is printing out and I'm supposed to type in something. So let's type in 0.3.1024. Okay, so the error was the enter values for A, B, and N wasn't showing, but it was basically saying, hey, you can enter values now. Why aren't you entering them? Because I never saw the instructions on the screen where I could enter them. Okay, there is one problem here where the values aren't working quite right. So, maybe I'll have to debug that some more. Give me a bit. Okay, there was nothing wrong with the code at all. I just said the interval was 0 to 0, so that meant an area of 0. But now that I have an area from 0 to 3, we are getting the same value as before, where we got 9 as our area. So it works. Let's do that again with a different area. I'm going to do 16 processes, and I want an interval from 0 to 10 using 2048 trapezoids. Now we have an area that's 333 and 1/3 units. So it works. Of course, we would like to double check this by punching this into an integration calculator or calculating it for ourselves. But now that we've shown that user input works, it works. So I tried it again with an interval from 0 to 1, and I got an area that is 1/3. So our program is working. So this is how we would do user input for an MPI program. One process receives input from the user, but then it must send that information to all other processes. So we would need a separate function for that kind of functionality, because only process 0 is allowed to use scanf. No other process can use that, so we need a function as a stand-in for all other processes to use scanf. In other words, one process uses scanf and then receives user input. One process uses scanf. All other processes can't and must wait for a message from one process that contains all of that user input. So that is the gist of what so that's the main point of, or as I should say, that is the main material for MPI for this week. Let's go back and look at the pthreads program for a little bit. So I'm going to pause the recording and go back to the pthreads program that we had a while back. So assignment 2 hinges on the programs from two of the PowerPoint files here, CSE-5250 chapter 4C and 4D, where we were looking at pthreads and how we could use pthreads for a pi calculation program. But we had a situation where two threads had to access the same variable, and we had to enforce mutual exclusion. So we did that using one of two ways: busy waiting, which is not recommended at all because the performance is terrible, and using something called a mutex. For each program, you're gonna try it with 1 million terms and 4 threads. But really, you can use any number of terms and any number of threads you want. It's just a matter of how patient you are with trying to wait for the program to finish. Especially when we're gonna use busy waiting. As I said, busy waiting. Don't use this in practice. The only reason we're using it here is to see how bad it is. So I have our pi calculation program that uses a mutex. So with the knowledge that we have from using the Civ program has us calculating execution times, and one way of doing that is explained in one of the slides where we have this, where we can use clock t begin equals clock, and clock t end equals clock. We would calculate the difference between the two, and that's our execution time. So really, all we gotta do for this program is add in a few extra lines of code, and then we can print out the execution time. So it will look something like this. I'm going to type in, well, I actually also need include time.h, and then I'm gonna need to type in type in clock underscore t begin equals clock. And at the end of the program, I can say clock t end equals clock. And then I can just type in time spent equals cast a double and minus begin divided by clocks per second. Alright, and then here I can finally type in time spent, save that. I can't build it because Visual Studio cannot recognize this pthread library, so I have to go through a different process of compiling and running the program. So I am going to open folder, open in File Explorer, go to this folder here, and there is our CPP file. I'm going to type in the command. I'm going to type in PowerShell into here, and then I need to compile this program. So give me a bit so I can look up the command for that. Okay, so the command to compile the program is shown here. It's gcc-g-wal-o. Name of the executable, and the name of the source code file. I entered that. And now I can run the program. So that would be /, since I named the executable pthreads, I need to type in /pthreads followed by the number of threads that I want. So I'm going to use 10 threads. And now we have an execution time of just under 1 second to run. So this is with using 10 million terms and using 10 threads using a mutex lock. If we did this, excuse me, sorry about that. So this is the gist of your next programming assignment. It's basically adding a few additions to the Pi calculation program that uses pthreads so that we can get an execution time. We would do this with both the program that uses a mutex lock and the other one that uses a busy waiting. If you recall from when I talked about this some time ago in a previous video, you may have seen how painful it was to run this program using busy waiting, because as some of you may have noticed, the video may have slowed down a lot. That's how abysmal it is to use busy waiting and why we generally never use busy waiting in a program. So this is your next programming assignment. I have it set to be due on November 10th here. So this goes for both sections. Though I have it tentatively set to be due next week, and that was because I gave out the assignment earlier this week, and I copied the module from one section to another. But if need be, I can push back the due date a little bit further. It's just that we have to move on so we can talk more about MPI, and then hopefully we can look into NVIDIA CUDA and see what that entails. So this is just a simple filler assignment where we play with the program, the Pi calculation program, get an execution time for that, and then we can compare the execution time for the program that uses busy waiting with that uses a mutex lock. And then we can see for ourselves, how bad is busy waiting anyway? Alright, so that is basically your next programming assignment. I showed the one that uses mutex locks because I did not want to go through the pain of doing that with a busy waiting. So get an execution time for both programs, and then that's basically your next homework assignment. Your next programming assignment will probably be based on MPI. So that's going to be it for this week. If you have any questions, you can email me. But if you have any other questions that require more than just a simple email, remember that you have the option to, it's never stated in the syllabus, but you have the option to schedule a Zoom meeting with me. The only thing that we need to do is agree on a time for that meeting. Alright, so that's going to be it for this week's video. Have a good week, and we'll pick up next week with more NPI related content. Thank you.